Okay, so this is a series of 2 talks about constraint satisfaction problems, but from a probabilistic combinatorics viewpoint. Okay, so I'll explain what this means. So let me first explain what is a constraint satisfaction problem. So the input is a set of variables. Let's say x1, x2 to xn. Okay, so for example, for example, our variables could be Boolean. And we also have a set of constraints. C1 to Cm. So each constraint is basically a set of variables along with some forbidden configurations. So for example, a constraint could be something like this. So this is a constraint that entails these 3 variables and forbids exactly one assignment. Okay, so this is a SAT constraint. Okay, and the goal is to, the goal is to find a satisfying assignment which basically means a configuration for the variables that satisfy every constraint. Okay, and so this was the example of satisfiability. Another example that we will care about is Q coloring of a graph. So the input here is a graph. We have one variable per edge, per vertex. We have Q values for each variable. We call them colors. And we have an edge per so we have an edge, a constraint per edge, sorry. And the constraint says my variables cannot take the same value. Okay, so we don't allow monochromatic edges. Okay, so for example, this is not allowed. Okay. So constraint satisfaction problems aren't be hard in general. So the direction we will take in this talk is basically identify interesting families of constraint satisfaction problems that have some property. Okay, so identify interesting families. So for example, what about Q coloring random graphs? So random graphs is an example of a family that is not worst case. So it could potentially have some structure. And another example is Q coloring, let's say, triangle-free graphs. So this is a deterministic family that has some restrictions on the input. Okay, and so this is roughly kind of what we want to do. In particular, in this, the plan is to cover basically roughly 2 topics. The first is a tool in probabilistic combinatorics called the Lovász local lemma. Okay. So this has connections to many things and has many applications in combinatorics, but I will care about its connections to local search algorithms. Okay, and then some cool applications. Another thing I will care about is random CSPs. And in particular, phase transitions. And algorithms for them. Okay, and I will try to draw a connection between algorithms for CSPs and the Lovász local lemma. Okay? So this is kind of the plan for these two talks. And today I will focus on the local lemma. Okay? Any questions so far? Cool. Okay, so what is the local lemma? So it was proved in the 70s by Lovász, and it's a powerful tool in probabilistic combinatorics with many, many applications. And here's roughly what it says. So imagine we have a family of events which we consider bad in a probability space. Okay, so as an example, imagine that we have a case in a formula, and we come up with a probability distribution over the binary cube. Okay, and now we have one bad event for each class, for each constraint. And the bad event says constraint CI is violated. Okay, so this is why it's a bad event, because we want to avoid it. And what we want to show is that with positive probability, we can avoid, all bad events. So if we sample from this probability space, then with some positive probability, we can avoid all bad events. Okay. In this example, this would imply that the formula is satisfiable, right? If we show that this is positive. Okay. Okay. So there are.
For like a random assignment.
Yeah. For example, yeah. Yeah. Right. But in general, from a sample from your probability space.
Right.
Okay. Cool. Okay, so here are two trivial ways to establish something like this. The first one is the union bound. Okay, so let's say that let's say that the maximum probability among these bad events was p, and let's say it's less than 1. Okay, so a trivial way to establish something like this is like to say that p times m, that is the number of constraints, is less than 1. Okay, so this is trivial, but the bad thing is that here p scales with m. Okay, and we would like a scale-free bound. Sorry. My bad. Okay, sorry. Yeah, we want to avoid any bad event happening. Okay. Yeah. So another trivial way which we can establish this is imagine that we had imagine that it was the case that all these bad events were independent. For example, we have the uniform probability distribution over the binary cube, and our clauses do not share variables. Okay, so and we have one bad event for each class. So now these are independent, okay, because they don't share variables, and this is a product distribution. So in this case, the probability of avoiding all bad events is at least 1 minus p2. Okay, it's exponentially small, but it's positive. And the bound is scale-free. So p has to be less than 1. Okay? So this is another trivial way to do so. And the local lemma is basically a way to relax this second way of proving that we can avoid all bad events. Okay? So it deals with a case where we have limited dependencies. Okay? So here's the statement. So assume that for each bad event there exists a set So for each bad event, basically we want it to be mutually independent from all but very few bad events that are contained in this set. Okay, so basically what we want is so di here is a set of specific bad events that are related to bi. Okay? And what we know, what this statement means is that for any other set of bad events, conditioning on them does not affect the probability of bi. So bi is independent of all bad events, but those in di. Okay? So for example, again, in the KCNF example, if your probability space is like uniform over the binary cube, and you have one bad event for each clause, then each clause is its bad event is mutually independent from all the other ones that correspond to clauses with that do not share variables with a clause. Okay, so the symmetric form of the LLL says basically that that if each bad event is mutually independent of all but at most delta other bad events, and it's not too likely, so under these two conditions, then the probability of avoiding all bad events is positive. What's what?
What is delta?
Delta here? It's a number that you give it as input to the theorem. And basically, it's a bound on the number of dependencies. Okay, so if you somehow can, I'll give an example, but if you somehow can ensure that its bad event does not depend on too many other bad events, so let's say at most delta, and p, remember p is the maximum probability over the bad events, times delta plus 1 times is plus 1, under those two conditions, yeah?
I think, can you remove the plus 1?
I mean, you can, but
Okay.
this is kind of the standard version.
Here is the number.
Yeah, so here is like 2.7.
EP delta at most 1 is enough, right?
Mm-hmm.
EP delta at most 1.
You mean like this?
Yeah, but and also now the plus 1. This is still true, right?
I think so, yeah.
Okay.
Yeah, but it involves, I mean, the classical proof gives something like this.
Yeah, sure.
If you want to, yeah, you have to do something more complicated. Okay. So, okay, let me show you an example. Example. So say you have a case in a formula, and it has the following property. It's sparse in the sense that each clause shares variables with at most 2 to the k over other clauses. Then this clause is satisfiable. Okay? Sorry. Right. Yeah. So a case in a formula is something like this. So basically, you have Boolean variables, and you have constraints, and each constraint forbids exactly one assignment. So
Such a bunch of odds, there are k of them, and then I have to.
yeah. Right. So each constraint has k variables, and just one of them, one of the 2 to the k assignments is violating. Okay? So how do you
This is actually the original application.
think?
Maybe different in languages, like two coloring or hypergraph.
Yeah. So it's yeah.
It's why it was made.
Right. Right. So the proof is very simple. You basically apply the local lemma with a uniform distribution over the configuration space.
Coloring is not exactly the same because you don't have U-turns, you have U-turns, but it's almost the same.
Yeah.
So for two coloring, the only difference
Okay, yeah.
is that instead of
Monotones, yeah.
No, it's different.
the only difference with two coloring is that each constraint forbids 2 assignments. That's the only difference. So instead of 2 to the k here, you get a 2 to the k minus 1. Otherwise, it's the same. Okay? Okay, so proof. We have one body event for each clause. And we want the uniform distribution over the binary cube. And then the probability of each body event is 1 over 2 to the k, right? Because there are 2 to the k assignments, and only one of them is violating. So if we flip random coins, then the probability that a body event is violated is 1 over 2 to the k. And because we know that each clause shares variables with fewer than this many clauses, we know that for each body event, the set di is basically less than 2 to the k over e. So this is the set of clauses that share variables with clause I. Okay, so these are the only dependent events. And basically, then you just apply this, and you are done.
Okay, you're going to run into a little bit of trouble with +1. But I will ignore that.
Here it's like strict.
But then there's no reason this is a big deal. But it's okay.
Did I mess?
Just replace e with a number slightly larger.
2 to the k minus 1. Or
Like this, maybe?
no, that's
No,
minus 2.
Just replace e with 2.8.
You should just put a floor.
Floor?
E with 2.8.
Like this? That's good now? Okay, cool.
Whatever.
Okay. Cool. Okay, and so I mean, this is the simplest form, the symmetric form. You can actually, people have developed many other versions of the local lemma, and here's kind of roughly the idea. So basically what we have here is, let's say, we call this a dependency graph. And it's over the set of, so its vertex set is the set of bad events, okay? So it's a directed graph. So for each bad event bi, its neighborhood is basically set, this set di, okay? So this is set di. And you do this for every bad event, and we call this a dependency graph. Okay. So the more involved versions have to do with what if, each bad event had a non-uniform probability. So what if we actually want to use the fact that for each bad event we know a bound on its probability and not a uniform bound. Okay? So for example, here's another version. So for example, if p is less than 1, this is again the uniform bound over all the probabilities of bad events. And for every I, so basically for each bad event, you sum over the probabilities of each neighborhood. If this is less than 1 over 4, then the same conclusion holds. Okay? And the nice thing about this theorem, I mean, there are other forms, but the reason I'm showing you this is because you can roughly think as the local lemma, I mean, heuristically, as a local union bound. Okay, so it's like saying that if you take a local union bound, right? So this is a union bound locally in the neighborhood of each bad event. If it locally holds that it's less than 1 over 4, then basically you get some global property. Yeah?
Why 1 over 4? Is the correct answer? Or?
Yeah, I think 1 over 4 is tight for this one.
Okay.
But the constant is not important. It's some constant less than 1.
Sure.
Okay, and for example, when the dependency graph, when the neighborhood becomes the whole set, then this is exactly this union bound up to a constant.
Yeah.
Okay, so I mean I think that's a nice way to think of it.
It's another weakening of.
Yeah. Yeah. So it's a weakening of this thing.
Yeah.
Right?
Yeah.
Okay, so that's cool. Okay, so this is, I mean, there are other, so for example, if you think of this digraph as being symmetric, then you can do many other versions that exploit the whole kind of information from the graph. But this is something we won't talk about it here. Now, the LLL has many applications in combinatorics, from, I don't know, Ramsey theory to designing error-correcting codes. And if you want to Lucas talk in this Fox event graph falsification, okay. And it's actually behind this super powerful method in graph theory that's called the Roydel method. or the semi-random method.
For the legal?
Yeah, yeah. So this thing, okay, so this method is behind some very strong results in graph theory. For example, a proof by Jeffkan that Goldberg-Seymour conjecture holds asymptotically. That list edge coloring conjecture holds asymptotically. Again, these are by Jeffkan, and these are super cool proofs. And total coloring conjecture. This is by Molloy and Reed. This by Ken. Coloring locally sparse graphs and many other things. So this is a very powerful tool, and I hope to show you some ideas behind it in the next talk. And so so these are some of the applications of the LLL, but it has, besides application, it has connections to many things. So for example, connections to local search, which will be kind of the theme of today's talk. And statistical physics. This is by Scott and Sokol, that basically say that roughly a condition for proving that the log partition function in some models is non-vanishing. It's kind of a local lemma criterion, so a completely different field. There's also a connection recently with algorithms that for sampling distribution or counting. So this is by Moitra and others. And there is even like a quantum version. And I guess others will follow, because at the end of the day, what the local lemma is an expression of a phenomenon that says when you have limited interactions, sometimes this is as good as having no interactions at all. Okay? So this appears in many fields, and kind of the local lemma, it has it's the proof that matters. It somehow counts how this interactions affect the system. So this counting, it appears in other forms in other fields. Okay? So this is why it appears everywhere. This is some vague statement, but yeah. Okay, so what I want to focus on is the connections between the local lemma and local search algorithms. Okay? So since it had so many applications, since the 70s, many people tried to give an algorithm that finds the solutions that the local lemma promises. Okay, and this started with the work of Beck in the 90s, and then by Alon and other people. But all these works in this first line of attempts did not give the correct bound. So they gave, for example, for the case of KCNF, they gave something like this at best. Okay, that the bound that you need for the degree is something like this. Okay, and then in 2008 there was a breakthrough by Moser. Okay, that showed that basically a very simple local search algorithm can go all the way. And he introduced this super cool argument called the entropy compression argument. Okay, so this name is by Tao, Terence Tao, where he blogged about it. And so besides capturing the local lemma, he introduced this very cool technique but other people used after him for to analyze other local search algorithms. And soon after, in 2009, Moser and Tardos basically make the local lemma constructive for any product distribution. Okay, so this would be a technique that works only for the KCNF, at least in the first form. And then Moser and Tardos using a different technique, also elegant. Anyway, it's called a backward-looking technique, but it's not important right now. So they managed to make the local lemma constructive whenever the underlying probability distribution in the configuration space is a product over independent variables. Okay, and then others. Okay, so and then other works followed, and I guess what I want to talk to you about today is how these techniques that followed Moser and Tardos have connections with a class of algorithms. I'm going to call them local search algorithms. And it's a general class, and it's as follows. So imagine that we have a state space omega. And in omega, we have a family of subsets of omega. Okay, we call them flaws. These are subsets of omega. Okay, so basically, you should think of them as bad events. But for now, because I'm going to describe an algorithm, there is no probability measure. Okay, we will see what the role of a probability measure is. But for now, I'm just calling them flaws, just to highlight the fact that this is an algorithm and not some probability space. Okay. So, question. So here's the algorithms we care about. So for each flaw fi and for each state that is contained in this flaw. So for example, okay, so let me give you an example. So in the KCNF example, fi would be the subcube of truth assignments that violate clause CI. Okay? So this would be the flaw in the case of KCNF. And now for each such truth assignment, we will have a distribution. And you should think of this distribution as a way to escape from this assignment in this state. So our algorithm, when it's in this state, sigma, where this flaw exists, where this clause is violated, will want to escape from it. Okay? So this is how it's going to do it. Okay? So it's going to use a distribution over that has to do with that depends on sigma, and basically, yeah, use it to go to the next state. I'll give an example, but okay, so this is kind of the setting, and here's the algorithm. Okay, so here's the class of algorithms, basically. So that's a good idea. Sorry. Okay, so here's a class of algorithms. So we start from an arbitrary state sigma 1. Okay? And then while the current state is flawed, okay, so we set while the current state is contained in one or more of these forbidden sets, or in other words, while valued constraints exist, if you will. Okay, so we focus on one. So let's say pick one. Let's say pick one, pick J, focus on one, and then sample the next state you sample it from this distribution that corresponds to the flaw of the constraint you picked. Does that make sense? And then you keep doing this until you hopefully reach a state where no flaw is present, where no constraint is violated. So this is kind of the class of algorithms that we care about. Yeah?
So is it guaranteed that this distribution, the output state, will satisfy this flaw, like flaw J?
No.
Need not be?
No.
Could still be like flawed for
Yeah.
the same constraint?
Yeah. Yes?
This probability distribution is basically the probability to go to any probability to go to any other state starting at sigma.
Yes. Right. So I'll give an example.
Any other state in Fi or any.
And this is up to the algorithm designer, any state. So this is any probability distribution to move in this configuration space. Okay. So I'll give an example to make this concrete. Okay, maybe here. Here's an example. It's again on KCNF. So, start at sigma 1. Here, sigma 1 is any configuration of a binary cube. Okay? And then while violated constraints exist, clauses. Okay, pick one. Pick one, say C. And then resample C. So resample is an instantiation of this probability distribution. Okay, and in this case, it could be something like if this is your clause, and it's variables, so there are 2 to the k possible assignments to the variables of the clause. Pick one at random. Okay, so this is what resample means here. Okay, so whenever you're at a state that violates a clause, what this distribution here, what it does, is it considers the 2 to the k possible states that result by mutating the variables of C, right? And it chooses one of them uniformly at random. For example, yeah. Did that make sense? Okay. But yeah.
Can't you randomize Moses' algorithm?
Yeah.
It's not possible, right?
It is possible.
Oh, it is possible.
Yeah. Under
Wait, do we think? Remind me if we think search P is equal to search PVP.
I don't know. Yes.
Okay.
So okay. So right. So what I'm going to do next is I'm going to show you an example of how this. Wait, where is it? Anyway, I'm going to show you an example of this entropy compression argument. Okay. So this is not the way we think of it. The thing of the analysis of the algorithms these days. but I'm going to show it to you for 3 reasons. Wait 1 second. One, it's super elegant, and if you haven't seen this, it's super cool. 2 is half of the proof, it will be reusable anyway, so it's not like I'm wasting your time. And 3 is unlike the next paper of Moser and Tardos, this entropy compression argument can generalize to this more general setting. Okay, so those are the 3 reasons. And maybe we should do a break now, and then I'll do the. I'm going to show you this entropy compression argument. By the way, the reason I made this kind of parenthesis and explained the general setting is that, for example, the entropy compression argument originally worked just for this algorithm for KCNF. And then only later in 2014, with Dimitri's, we showed that it kind of works for this general setting when the distributions are uniform, so when it's a directed random walk. So it had to be uniform for this to work. And so I'm going to show you later developments where we can do basically analyze any such algorithm, right, and show you applications of this. But the connection of the local lemma is with this general setting, right? So there's a strong connection. Basically, you can see every application of the local lemma as applying such an algorithm, and any such algorithm you can see it through the local lemma in a way. I'll explain that, okay? But for now, let me show you this entropy compression argument, which is so we will use it to analyze this algorithm, okay? So this algorithm is basically the same as this algorithm, but I have chosen a specific way to pick which clause to resample at each step. And the idea is that this will help me with counting, and this is kind of a counting, this is like kind of a counting argument at some point that I will use in later proofs. So I'll do it once here, and then I can, and you can believe me later, okay? So, so what is this way to pick a clause at each step? It's kind of a recursive way. It's kind of like doing a DFS in the graph that is induced over the set of clauses and where each edge corresponds to variable sharing.
Is this fixed C or C prime?
Fixed C prime, sorry. OK. OK, so what does the algorithm does? OK, so now we will analyze this algorithm, which is basically an instantiation of this one. So it has this global procedure, which is called eliminate. And that says the following: while valid clauses exist, pick one, say the lowest index one. OK? And once you pick a clause, what you do is, the first thing is you resample it. OK? And then you check in its neighborhood. By neighborhood, I mean the clauses that it shares variables with. OK? And while there exist clauses in the neighborhood of C that are violated, you pick the lowest index one again of them, C prime, and you repeat the process. OK, so what I've done here is basically the algorithm is, again, resampled clauses, but I'm doing this this kind of sophisticated recursive way. OK? This is just to make the proof easier. Yeah.
So you're trying to pick a random assignment.
Mm-hmm.
You're trying to see if this KCNF is satisfiable or not.
Yeah. So
and you're trying to search for a satisfying result.
right.
Now, if you take a random KCNF, what do you expect? Is it going to be satisfiable, or is it easy to check whether it's satisfiable or not?
For random KCNF?
Yeah.
So for random KCNF, whether it is satisfiable or not, this depends on the ratio between the number of clauses to the number of variables. And there is a kind of sharp phase transition. So when the density is above some point, then you know it's unsatisfiable with high probability. While here, for sparser cases, it's satisfiable with high probability. But these are not random KCNF. So these are case NF that are sparse. They're deterministic but sparse. So have this property that each clause shares variables with at most too many other clauses. Okay, and yeah?
Question. So, like, are you picking against C prime the lowest index one?
Yeah. Okay.
I don't understand. So you're trying to resample C, and then, okay, you find something that's the same. What do you mean by fix it? Do the same thing again?
Yes. Fix C prime though.
At what point do you get back into this global?
When this while it's not longer true. So when nothing in my neighborhood is violated.
Of C7 prime or whatever.
Yeah.
C.
You resampled C, so
Yeah.
now this affects all the other clauses detach the variables of C.
Right.
So maybe there are, after you resample, maybe all these clauses are already satisfied.
Okay.
Then you're done.
Okay. And if they're not,
Then you need to go to the lowest index one and do the same thing for that.
and then you check whether the neighborhood of that lowest index one.
Yeah.
is satisfied.
That's why you said it's a DFS. You kind of keep going.
Yeah.
Oh, I see.
Any other questions?
So these are neighborhoods of C and not like sub-variables of C.
You mean DC here?
Yes.
So DC here is the set of clauses that share variables with C. Yeah.
If you resample C and again you get the same bad thing, you just resample it again, like.
Yes.
Okay.
I mean,
That is something.
you resample C, no matter what you get, you look at the neighborhood. This includes C, right?
Sure.
And you take the lowest index one there.
Okay. So
It might not be C.
You still didn't fix C, but
Yeah.
you just pick a different
Yeah.
one. Okay, fine. This is low enough probably. Okay.
So in Mozart Dash is fine to remember. So it's not only that you fix the neighbors, but then if neighbors of the neighbors were broken, you're also going down there. You kind of fix the whole
Yeah.
That's
kind
what
of
he
branch
That's
of.
what it's doing. Yeah, that's what you already said, DFS.
Yeah, but if you say just fix, so while there exists one among those dependent
But
on
you
C.
return from the recursion,
Well,
right?
then you
It's
take
DFS.
you take C prime. You put C prime to be C or something. C to be C prime. Or-
You write C prime more dominantly in there. Yeah, thanks. Does that help?
Right. Yes. Now it makes sense.
Sorry about that. Okay.
The prime was not a good size.
I think what you should think of it as this is a funny way of picking which. I mean, think of this algorithm that picks a clause to resample. This is a funny way of picking one that will help me with accounting. Okay, so I don't have to do funny stuff.
I see. So another algorithm would be
Anything works.
pick C at random every time.
Yeah, this works. Yeah. Basically, for this particular algorithm, anything works. For this particular argument, this is what. Yeah. Okay. Cool. Okay. So here's the argument. Okay. So I want to prove that this thing terminates. Okay. So I'm gonna run my algorithm for t steps. Okay. And I'll show that while t grows to infinity, this thing will have to terminate. Here's how I'm going to do that. Okay, so I imagine that before I even start running the algorithm, I choose kt random bits beforehand. Okay, so let's say k. So I sample kt random bits. Now, after I have done that, basically my algorithm becomes deterministic, given the string. So every time I want to, so this is where the randomness is used. This is the only part where I use randomness in the algorithm. And every time I want to resample a clause, I basically read the next k bits and I use them as new values for the variables of the class. Okay? So this is what I'm going to do. Now, to prove that the algorithm terminates, okay, I'm going to show the following. So that if the algorithm has not terminated in t steps, okay, so assume that this is true, that the algorithm has not terminated in t steps, give me a second, then I will be able to produce a log of the execution. Think of it as a mapping from the binary string I read to some other binary string, okay, that has the following property. I'm going to call this the log of the execution. Okay, so L of sigma, so sigma is this random bit, this random string, I'm sorry, that has length kt. So L of sigma, I'm going to prove that it has two properties. So property 1 is that its length will be at most lambda t plus beta, where this is a constant and lambda is something that's less than k. Strictly less. Okay? And then, so this is property number 1. Property number 2 is that given L of sigma, I can get sigma back. So this is a lossless compression. So given L of sigma, I can uniquely reconstruct sigma. Does that make sense? OK. So what's the problem with that if I manage to show this? OK, so remember here lambda is less than t. OK, so at some point when t grows, the length of sigma, so kt, at some point will be more than lambda t plus beta. Okay, because this string grows with some factor less than k. Right? But this will mean by the second property that I have found a way to losslessly compress random bits using less than. So I have found a way to compress a string of kt random bits using less than kt random bits, which is information theoretically impossible. Does that make sense? So the algorithm has to stop.
So why does that, okay, so why have you compressed exactly?
This is, you should think of this as a compression scheme. So this compresses, I mean, when for large enough t, this thing starts to compress.
It's lossless, okay.
Okay, so this is kind of impossible.
Can I just think of lambda like k over 2 or something?
Lambda would be,
It can be 0.99. It doesn't have to
yeah, it's something 1 minus epsilon k.
Okay, F1 bounded away from 0.
Yeah,
Okay.
from 1. By
So
way
that
from 1.
means it'll be like linear or something, the algorithm, right?
Yeah, the algorithm will be linear.
Okay.
I mean, it will depend on beta, but beta here will be linear.
Okay, not too large, so
Yeah.
it'll be linear.
Okay.
Very nice.
So this is kind of the argument, and this is, a kind of cool argument. Okay. So here's a way to make it less cool. I mean, to say, to say this in kind of plain words and not like compression. So so you have like basically. So what does this mean here? So what you show here is that you pick one random string and you put it at random. Okay. So there are 2 to the k t random strings. Sorry. You pick one at random. Right. What this does is basically it counts how many of these strings lead to a failure, to a no termination. So basically, So these are all strings, so the bad strings. Okay, so the bad strings are at most, 2 to the lambda t plus beta. Okay, this is what it means to compress under this assumption. Okay, so as long as the algorithm has not terminated, I'm able to compress. So I'm basically counting the strings that are bad, that do not lead to termination. Okay, so now the probability that the algorithm fails is okay. So this is the probability that the algorithm fails. So at some point when this becomes more than beta, so this is positive, right? So when this becomes more than beta, the probability that the algorithm fails after this point on drops exponentially with every step you make. Okay? So this is what this is like to demystify this thing. Cool? Yeah, question.
I don't see how that L is a compression scheme. Can you?
Why is this a compression scheme?
Yeah.
Because if lambda, so it's a compression scheme for two reasons. Because lambda here is less than k.
Okay.
So eventually the length of sigma, which is kt, will be more than lambda t. And it's a compression because given sigma, given L of sigma, I can get sigma back.
Why do you write this L of sigma map to 0, 1 star?
This is a binary string. This is what I'm saying.
Subset of 0, 1 star. What you should be writing.
L of sigma is just
It's
like
just one string.
Yeah, it's a one string.
So L maps.
Belongs to 0, 1 star.
Yeah, so using the arrow here for me can recover from and also phrase it.
Just-
Yeah, sorry, not
oh, okay, I'm just confused because
Anyway, this is clear, right? You have
Yeah.
this many strings, only a few of them are bad, means you succeed.
Uh-huh.
and then I'm just confused because it's also length and
It's not a line.
L
it's a
of
mapping.
sigma is at most lambda t plus b.
Oh, with you
Ah.
need this.
I'm sorry. You're right. I'm sorry.
And L is just length, so I was
Yeah, you're right. You're right. This is bad notation. You're right.
It's also log.
yeah.
Yeah, it's for logged. Yeah.
For
Yeah.
not logarithm, but
Yeah.
Log.
what is log? Is it short for something?
Wood.
Log.
No, I think
Okay, fine.
Throw it.
I think
Please,
log of the execute. I think
log of the
yeah.
execution. Where does the word come from? But never mind.
I don't know. I'm not-
Transcript. Use the
Transcript. Yeah. They call it log. Yeah.
This case, we know how to de-randomize it? Like,
In certain cases, I mean, for this algorithm, yeah. This particular algorithm, yeah. Not all the LLL-related algorithms in general.
whose result is that?
For even in the original proof by Moser and others, they had an algorithm that is exponential, that de-randomizes it, but it's exponential on k. So it runs, to, I mean, if k is a constant, it's polynomial time. Okay?
So even till now, I guess pretty much we need that condition that k should be like a constant.
No, we can do fun stuff. Yeah.
Are you showing us the L?
Sorry?
Are you going to show
Yeah.
us?
So what kind of B do you get? Like T is
I'll show you. Okay. I'll show you exactly what's this thing. Okay. So here's
So
not this. Ah, well.
So the upshot of this analysis is that for some number t, you will be able to fix everything with high probability.
Yes. Yes. Okay. Cool. So right. So what is L of sigma? Okay. So what I will be writing down. So I will be writing down two things. First thing is the final configuration, final state.
Where B comes from.
Yeah. Well, part of it. Yeah. One part of it is this, and the other part is the sequence of clauses that is sampled so far. Okay, I mean, so the algorithm has run t steps and has not terminated, which means at every step there is a clause that gets resampled. Okay, so my log will be the set of these clauses. Yeah, so W is for witness here. Okay.
T should be subscript. WT.
Oh yeah. And the final state. Okay. So this will be my log.
State is just an ended string?
Yeah, the final configuration. Does that make sense? Okay, so we need to prove two things. The first thing is that given this string, I can get back the original random string that I used. And the second thing is that how to encode this efficiently. Okay? So So first of all, there's a reconstruction. Okay, so the reconstruction part is actually easy. Okay, so we have the final state t written down. Okay, so this we have, and now we know that the clause that was resampled before this final step was WT, because we have all written this down as well. Okay? But what do we know? Okay, so now we are trying to guess so what I'm trying to do is guess the trajectory so far. Okay, given my log. And using the trajectory, I can recover the random bits. But let's see how I can get the trajectory back. Okay? Okay, so this I had, and I want to guess what this is. Okay? Here's the point. So here's what I know. Let's say that this is sigma tau. Okay, and let's say that this is sigma tau minus 1. Okay, so what do I know about these two states? Basically, let's say that these are the variables of WT. Okay, what I know is that so these are the variables of this class WT. What I know is that I went from this state to this state by changing the variables of WT. So WT was violated, and I changed a few things. Okay? So this means that every variable in here is the same as every variable in here. This has not changed. Okay? Now, so the only thing I have to guess is what is the assignment for the variables of WT? What is it? Can anyone guess? There's one only way. So this is uniquely defined as well, because of the nature of KSAT. Okay? There was only one way with which WT could be violated, and so now I can guess. Okay, so this is a one-to-one mapping from.
So two ways you would add that to your log, and
Yeah, I would add the two. So my log would be an extra string that I.
so how would it?
Yeah. For example. Okay. So for example, yeah. Okay. So doing this, I can get the trajectory back, and so I can get every sigma back. And having the trajectory, I can guess the random bits, because I see how two states different, and now I guess how the random bits changed. Did that make sense? Okay, cool. Okay, so this was kind of the reconstruction part. So this is 2. And now let's see how we can encode this efficiently. Okay. KT.
Right now.
Why KT?
Because each WI is size K, no?
You need to encode the clause though.
Oh,
Yeah. So the naive way to do it would be use log bits for each clause.
And after you know the first one, the next one is a neighbor.
Right.
So kind of you want to use that. That's the idea. It's not exactly like that, but that's a split, yeah.
Oh,
It's not true that every two consecutive clauses here are neighbors, but something, yeah, it might jump back, okay? Okay, so here's how we encode the sequence, okay? So, so what I'm drawing here is the kind of the recursion forest of this procedure. So this is a forest that has one node for each clause I ever resampled, and it kind of follows the recursive algorithm, right? So let's say that W1 was the first clause we fixed, and let's say that this invoked recursively a fixed procedure on W2, and this invoked a fixed procedure on W3, and then this stopped, and maybe W4, and then this stopped, and W5, and then this stopped, and W6. Okay, so this is what I'm drawing here. Okay?
So it's maybe labeled with the same clause.
Yeah.
Okay.
So this is the recursive forest. Okay? So notice that if I know the forest, if I know what the forest is, then I can get the sequence back. How I can get it? Basically, I do DFS in the forest to get it back. Okay? So I just have to encode the forests.
Everything's okay.
Did that make sense?
Yeah, if there's like an ordering, or the ordering just by the indices, like, you know, if I hit the forest. Okay, you go to the lowest.
Yeah. I just do a DFS with choosing the lowest index clause at each step. I just basically follow the procedure. This is what I do.
And these guys are rooted, right? Like the top guys are rooted or something.
The top guy is the lowest index again.
Oh.
Among the top guys, it's the lowest index.
Okay, fine.
Okay? So if I have the recursive forest, I can get back the sequence. So now I need to see how to encode the recursive forest, right? So, okay, so basically, okay, there is a way to map these things to delta forests with at most m roots, which would mean that the number of such forests is at most 2 to the m times e times delta to the power of t. Right, so I want to take the log of that. I mean, this is what I'm going to show you, okay? So I would like to take the log of that, so this would be m plus t times log e times delta bits to encode a thing like this. Okay, so overall b, so I said I'm going to do a b plus lambda t scheme. So b would be this m plus this n for the final state. And lambda here would be less than k whenever e times delta is, whenever log e times delta is less than k. So when e times delta is less than 2 to the k. So delta plus 1 here. Plus 1. Okay? Okay, so this is I mean, what you can do. I'm going to show something easier, okay, just in the interest of time. And I get where I get a 2 here instead of an e. Okay, so the final condition will become 4 here. Okay, but this will speed up the process. So here's the point. So first, I will encode the roots of the forest. Okay, so I'm claiming that I only need
E by 2, so you
by 4.
by 4,
Sorry, by 4.
Oh yeah.
Yeah. So
Waste of time. I show you better one.
yeah.
False sound, right?
The log of 4 is 2. So right. So I'm claiming that you need m bits to encode the roots. Okay, and why is that? Why do we have? Okay, so sorry, m bits for the roots. Okay, why is that? I'm claiming that this, like the roots here, are a subset of the clauses, so there are no repetitions. Okay, so there are at most 2 to the m possible subsets, so I need m of them. Okay, so m bits to encode it. So why are there no repetitions here? Because if you oh, hold on. Yeah, I have erased the algorithm, but let me remind you. So the algorithm was something like you have this eliminate process, right? And you pick the lowest index one, and then you fix C. Okay? So the roots, and then you have this procedure fix. So the roots correspond to invocations of the fixed procedure from like the global thing, right? Okay. So we have one root for each invocation. Why can't we have 2 invocations with the same clause? Well, because let's say the first clause was C1, so we fix C1, right? When this thing returns, so it does what it does, what it returns, then what do we know about C1? It has to be satisfied, right? Otherwise, it would not escape this loop. Okay. So now, okay. So let's say this is C1. For sure, the next thing is not C1. Now, let's say the next thing is C2. Now I invoke C2 here, right? It does its stuff. Can it be that in the returning assignment C1 is violated? The answer is no, because if it was violated at some point, the clause that it would violate it would share variables with some other clause. So it would be in the fixed procedure of some other clause. And so it could not escape from that. Okay, so basically, once you call something from the global procedure, this gets fixed for life. Okay. So this is why the roots are distinct here. So this is why you have to do the m possible choices for what the roots are.
So you're telling me that basically in each rooted tree, after that rooted tree is done, everything in it is fixed. Everything in it.
Yes.
Okay.
And it will stay fixed. I mean, it will stay fixed.
Well, it could get unfixed.
Yeah.
But okay.
Yeah.
And okay.
M is the number of clauses, right?
M is the number of clauses. Okay. An identical argument will show you that for every set of so for every node and for every set of children, an identical argument shows that these guys are distinct. Okay. So I mean this. So you have at most delta of them. Okay. So right. So yeah. So okay. So how you encode this thing? So
you just found the depth of the tree or something. Like
so you use m bits for the root, and then you use 2 times t bits to encode the structure of the tree. What do I mean by structure? So if the tree, let's say it's like this, I want to encode the structure without the labels. Okay, so I write down something like this: parenthesis, 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 closing parenthesis, opening parenthesis, close parenthesis, close parenthesis. Okay, so I use this DFS kind of parenthesis trick to use 2t bits to encode the unlabeled structure of these things. Then now that I have the unlabeled structure, I use t log delta bits to encode the labels. So every time, so I know the roots, right? So I know the label of the roots, and I also know the unlabeled structure. So now I know what is, the left child by reading the first log delta bits in the string. It should be some neighbor, right? So there are delta of them. So with log delta bits, I can encode this thing, and so on and so forth. Because I know because from this 2D thing, I know the unlabeled structure. Yeah.
Do we really need to know the encoding here? Like trees, right?
right,
Take
right.
the log of that, and there exists an encoding which
Yeah, but I had to show you that
size.
it's kind of subtle. I had to show that that using any delta tree, you can get back very recursive. I mean, it's not very hard, but this is easier, I think. Okay.
So how many? So you didn't use as many bits as you said you would have to in the bad case, right? You
How about 2 here? While as opposed to log e, if I use the best bound. So this is why I get a 4 instead of an e. Okay.
Okay. I mean,
Somehow you don't.
M plus p times log delta plus 2 instead of plus. Right. Okay.
It doesn't matter.
It's not super important. Okay, and also there exist much more sophisticated counting techniques that can account for, what happens if, let's say, each clause has different length and draws. So every time it resample, it reads more bits and stuff like that. Okay.
Yeah, I agree. This gets more. Okay. Yeah.
And kind of this idea can generalize to basically any random walk on abstract spaces. Okay. So this kind of was able to prove the local lemma. I mean, make applications of the local lemma constructive in spaces where that are non-product distributions.
This is the work that you did with
Yeah. So this kind of also my was kind of the first thing I ever did.
You actually almost like M plus some smaller constant times t bits to encode the structure of the tree. Is that actually what's?
Yep.
Why do you say number 2? Just say something.
So in general, you don't need.
It's
So
like
so
4 to the t is the upper bound on the number
on the number of these
trees
strings.
on t vertices. So this is where this 2t.
But it
For
actually is
example.
lower.
No, the point is that you don't need to encode the structure of the tree and the labels independently. You can do it at once.
Oh, okay.
Yeah.
Oh, okay.
Moreover, there are like more generalized constructions where you don't need to know that each clause reads k random bits at every step. So you kind of combine the two, and then you don't even need clauses. You just need random walks. Okay, so that's kind of the idea. Okay, so right. Okay, so this kind of proof, it kind of does not generalize to distributions that are non-uniform. Okay, so for example, if let's say instead of the uniform distribution in the binary cube, you had another product distribution, so you had like biased coins, this thing doesn't work. Okay, and this was kind of the contribution of Moser and Tardo, the next paper. They showed how you can do this with another argument for any distribution, for any product distribution. Okay.
You mean what doesn't work is that the counting is not good enough.
It's not this part of the counting. This kind of always remains the same.
Which part messes up exactly?
I mean, this argument that, for example, what I said is that you need kt random bits before you start the algorithm, right? If the coins are biased,
It's fewer, right?
you need many fewer.
So
But it's not the entropy. But it's not about the entropy of this thing that's important. It's how they bias the space, kind of. So the LLL, it can apply very nicely with very low entropy, but this proof will not understand it, kind of. Okay, because
so you need to look at the entropy.
the entropy is not kind of the right thing to do if you want to go beyond uniform spaces.
Oh, wait.
If you do some kind of counting, different counting,
I mean, in a sense, everything is counting.
they also build this
they do kind of a more detailed analysis. And what they do is they try to actually bound what is the probability that event, that clause C is resampled at step T for any C and every T. They kind of bound this thing. And they have like, to do this, they build kind of some trees that grow backward in time.
They do some weighted count of these trees.
Yeah, but the hard thing is not to do the counting. This we know. The hard thing is to show why the probability of this tree, for example, is the product of the probabilities over the labels of the tree.
Sure. So it is a weighted count. Like you weight the trees by their probability.
Yeah, but why
Right.
can you okay.
Why?
I mean, I'll show you kind of a way to do all these things at once. Okay. So okay. Let me tell you what I'm going to show you now. Okay. So there was this entropy compression technique. And then there was this backward analysis. So this applies to uniform distributions. And then there is this backward analysis. Okay. That is by Moser and Tardos. And applies to product distributions, but any distribution. Okay, and then this inspired some work regarding not just convergence results, but also properties beyond convergence. So, for example, how the algorithm hits the solution space and stuff like that. And then there was this forward analysis. Okay, so by several people, including Harvey and Vontrack, and then kind of a paper with Dimitris and Vladimir Kolmogorov, that basically allows us to analyze this kind of walks for any kind of distribution that you choose, and we could use that to get basically applications to make constructive basically every LLL application that's out there. But in general, to analyze, local source algorithms. So this would be this kind of works where like a criterion that says, give me an algorithm. I give you a kind of, I look at the algorithm and then I give you a criterion to analyze it. So if the algorithm passes this criterion, then it will converge. And it turns out that the criterion we used, we kind of later understand that it connects to the local lemma in a specific way. So this is what happened here. I'm telling you the story briefly. And now, kind of all these things, there is a way to see them as bounding norms. Bounding norms of matrices. Right? And not only you can capture everything, but you can also kind of get more out of it, more refined conditions, and better analysis of local source algorithms. Okay, so this is what I'll try to show you. And the reason why this thing, it does not generalize that easily, is basically it kind of, in hindsight, it requires, in this analysis, some of these matrices to be commutative, to commute, while the other things do not need this. Anyway, this is why I was not telling you what happens here. But kind of this is the story, a brief, like the history so far, and I'm going to explain exactly what happens. Did that make sense? OK. So So now here's the setting. Let's forget about the local lemma for a while. So we have a general algorithm, like the one I showed you. So that is, we have a set of flaws, f1 to fm. And we have resampling distributions for each flaw. Okay? And we try to analyze this kind of algorithms. While flaws exist, focus on one and try to fix it using this distribution. Okay? For now, you can think of the way we pick flaws as this recursive procedure. Okay? So to make things concrete. Okay. So now, what I want to so now I want to explain kind of this result. Okay, which basically you can use to capture all the standard LLL applications. And it's a result that says, give me an algorithm, I'll give you a sufficient condition for it to converge. Okay? So here's the condition. So the first thing you do is, as in the local lemma, you introduce a probability distribution mu from the configuration space to 0, 1. So this is a probability distribution. Okay? And then you measure the performance of the algorithm using these two quantities. Okay? The first one is kind of weird, but I'm going to explain it. It's called the charge of the flaw. And it's the following. Okay? So this is what you do. So this is what you compute. So I mean, I'll give an explanation, several interpretations of what this means. But for now, just to parse it, so you go at every state tau, and then you look at all the incoming transitions to tau that come from attempting to fix a flaw fi. And you weight, so you consider this kind of weighted in degree, where the weight of each arrow is basically the kind of the potential drop times the probability of the transition. So you can imagine that. So we have, we have a probability distribution over the space. Okay. So it assigns mass to every probability mass to every state. So what this charge here amounts to is counting, the weighted in degree for each state and taking the max. By in degree, I mean all the states, or all the transitions that come to tau when we attempt to fix flaw fi. Okay? I mean, I know this doesn't make sense. I mean, intuitive sense right now, but just for you to parse it. Okay? Yeah.
What exactly is the goal? I mean, so we have a bunch of constraints. This is just a CSP or something.
Yeah, it could be a CSP, but in general, it's.
Like, is it monotone? Should I have a preference between 0 and 1, or?
What is 0 and 1?
You have
So this is a general probability distribution that assigns to any sigma in omega a number in 0, 1. This is, yeah. So it's not brackets, right? It's a real number. So this is a probability. I'm not saying something fancy here.
These are like satisfying properly.
Yeah.
Oh, okay.
So it's like the local lemma where you choose a probability distribution over the space. I just call it mu.
Why do you divide by mu of tau?
I will see. Okay. I mean, this has several interpretations, but yeah, for now, okay, let's state kind of the theorem. Okay. So the second, this is the first ingredient. Okay. So the second ingredient is the following. So you define this notion of causality between flaws. It kind of plays a similar role, and in hindsight, the same role as dependencies in the local lemma. Okay? So we say that a clause I potentially causes a clause J, a float J, if there is a transition in the algorithm where, Fj is not present, and then you take a step with trying to fix I, to fix Fi, and now you reach a state and Fj is present. Okay, so this is what I mean by when I say flow I causes flow J. Okay, and also this is like a corner case. If there's a transition in which we attempt to fix clause I and we flow I and we fail, then we say that flow I causes itself. Okay, this is kind of a corner case. So this induces a directed graph over the set of flaws. Okay, and now the condition is it's like a local lemma condition. Say that gamma is the maximum of these charges, and say that
The graph depends on the graph depends on
the graph depends on the algorithm, just on the algorithm.
Okay. Why?
Here-
Okay.
Here's how this graph is defined. Okay, so you have one vertex for each flaw. Okay, one vertex for each clause equivalent. It's a 1, 2, 3, and 4. And then you add an edge in this graph. If you look at your algorithm and you say, well, there is a chance that I take a transition in which I attempt to fix I, and in this attempt I introduce 2. Yeah.
Like even if there's one way to do it.
Yeah, there's one way to do it.
Okay. Wow.
Okay?
But like in the previous algorithm that we saw, since it's recursive, then
So in the previous algorithm, what are the distributions? It's you have like a clause, and you change its variables. Okay, so you only change the variables of the clause.
no, but you change and then you go to another neighboring.
But this has only to do with how you pick flaws. It doesn't have to do with the when I say causes, I mean I just look at the probability distributions here.
You mean in one step?
Yeah, yeah.
Right. Moving from sigma to tau.
Yes.
Not eventually.
Yeah, not eventually. In one step.
So there it was just those that share variables.
Yeah, exactly. Those that share variables. And in fact, it's something more refined if they share variables, but they want it the same way. They want the literals the same way. So there is no way that one causes the other. For example, okay?
Really?
So let's say that you have two. I mean, it's not super important, but let's say that you have two clauses C1 and C2, and they just share one variable.
Could be when I fixed C1,
Uh,
I ruined that variable even though I did fix C1.
So what I mean, it's not a good example. What I mean is you only care about transitions where you don't care about reaching a state where C2 is eventually violated. You care about if you were the one to break it. So it could be cases where C1 and C2 are both violated in a state, right? But it could be that if I think about it and play with the literals, it could be, yeah, it's not super important. Okay, so so here's the theorem. You look at this quantity, which is the maximum of the charges, and then you want to bound what is the neighborhood in this graph. Okay, and then if gamma times delta times c is less than 1, then you're guaranteed that your algorithm converges. Okay, so this is kind of the theorem. And then you can get any other form of the local lemma, you can get it here. Okay? Other questions? Yeah.
Sorry, I got confused between mu and p. Is there a connection? Like, how are you trying to fix like p some arbitrary distribution, or is it connected to mu?
So the mu does not appear in the algorithm. It's just for the analysis. Mu, it's It's a probability distribution in the space, and the only reason I use it is to define these charges. It's like a way to measure the performance of the algorithm. Okay, that has nothing to do with the algorithm. So this is, it only comes later. Okay, when you're trying to apply this theorem. So you can apply this theorem, choosing two different measures and get two different results. That makes sense? And did the theorem make sense? Okay. So
Gamma is the size of causality.
gamma I is, yeah, so I call by gamma I the neighborhood of flow I in the graph. Okay? Yeah. Yeah. So I guess what I'm going to do now is give you interpretation for what this is. Okay?
Why you divide it as
Okay. So there are three interpretations of this quantities here. Two of them are algorithmic, and one of them relates it to the local lemma. Okay? So let's see the first one, the first algorithmic one. Okay? And it was kind of the way we were thinking about it in the kind of original proofs. Okay? So what is gamma of I? So here's a way to write it down. Okay, so what I've done here is basically I multiplied and divided by the probability of the flaw under the measure. Mu. Okay? This is what I've done here. Nothing much. So these charts here is the probability of the flaw under the measure, as in the local lemma, times some factor. Okay? So now I'm going to interpret this factor as a measure between the actions of the algorithm and the distribution mu. So the idea is that we would like the algorithm to kind of, we would like the distributions that come from the actions of the algorithm to be close to mu. And this expression here is a measure for how to do that, for how to count this distance between the two distributions. So let me be more specific.
So it kind of looks like a divergence. They're like information. Are you thinking about it that way?
Sorry?
I said this quantity just looks kind of like a divergence.
Yeah, it's meant to measure the distance between the. I'll show you. Okay.
Yeah.
So here's what this thing is. So think of the following experiment. Okay. So the first step of the experiment is that you sample a state sigma. So you sample a random state that violates clause Ci. So a random state in Fi. By random, I mean according to mu. Okay? And then you take a step with an algorithm to get a distribution tau, to take a state tau that comes from this distribution. So I take a step in a random state that violates Phi, and let's say that tau is the distribution. Tau is the resulting state, and let's call nu the distribution on tau. I'll say it again. So basically what I'm doing here is I look at the distribution that is induced by the actions of the algorithm when I address Fi at a random state. By random, I mean random conditional to mu. Sorry, according to mu, conditional to phi. Okay, so this is what comes out of the algorithm. Okay? Okay. So I'm claiming that nu of tau is exactly this thing here. And why is that? Is because I choose a state, sigma, conditional on phi being present, and I take a stop. So this is what I just described in the experiment. This is nu of tau. And so now what this thing does, what this expression does, it's equal to nu tau over mu tau, right? And we take a maximum here, sorry, not a maximum tau. So it's a way to see how these distributions differ in the worst case. It's the worst case ratio, basically, between nu, which is a distribution that comes from the actions of the algorithm, and mu, which is a probability distribution that I chose. Okay? And the more compatible, so this ratio is always more than 1 if the distributions are different. And the idea is that the more compatible the algorithm is with mu, the better bound you get for gamma y. Okay, so so overall you get something that is nu phi times a distortion factor. Okay, and this distortion factor is this ratio, and it measures the kind of like compatibility between the two. Okay, now let's see an example. Okay.
So in other words, if you want to analyze the algorithm, the best for you is to choose mu that is compatible with the algorithm.
Yes. Yeah. I mean, we'll see there are trade-offs. We will see what's going on. But let's see an example where this thing works perfectly. And this example is the, I guess I'll finish with that. And this is kind of the Moser-Tardos algorithm example we saw. OK, let's see what this experiment gives there. So, OK, so this is, let's say that this is a set of all n variables. OK? And let's say that this is clause Ci. OK, so what was my experiment? It was, the first step is I sample distribution, I take a sample from the uniform distribution conditional on that Ci is violated. OK, so everything here is random, basically. And now this is violated. OK? And then I take a step with my algorithm. OK? So now what happens? What is the resulting distribution? Because my algorithm basically flips a coin for one of these bits, this becomes random again. So everything is random. So what I get here, what nu is here, is basically the uniform distribution over the space. Okay, so it's mu. So this works perfectly. So this is 1 in this case, right? And when this happens, we call this a resampling oracle. Okay, and this was kind of a notion introduced by Harvey and Woodruff. Okay. So this is an example. Oh, sorry, Harvey and Woodruff. And OK, so this is in 2015, and there was this paper by Dimitris and I in 14. And what this paper does, is kind of combines them in a way. OK. So OK. So one way to interpret things is to interpret this thing as a measure of compatibility between the measure and the actions of the algorithm. OK? And here's a so here's an example. I'm claiming that there is always a way to make this to be equals mu phi. There is always a trivial way to make this p equal to mu fi. So let's say I want to design an algorithm that wants to minimize this expression here. I give you a mu, and I want to come up with rho i's or pi's that minimize this expression here so that this ratio is always 1. Okay, what's a way to do that? A trivial way to do that. So it's simple. I just sample from the measure, okay? So my actions could be I just sample from the measure, okay? Why it's not a good idea? Because if you just sample from the measure, first of all, this is a silly algorithm. Why is this a silly algorithm in the eyes of our analysis? Is because it makes this causality graph huge. Because when you sample from the start, when you just restart, you might cause everything. So what would you like to do is to have distributions and algorithms that kind of locally regenerate. So given a conditionally random sample, they can uncondition, kind of local, by doing local moves. And this is why it's local search. Okay? So to give you a final example of this, and then in the next talk I'll explain how this connects to ELLL. So there is there is, as I told you, these two papers by Jeff Kahn that have to do with Goldberg-Simul conjecture and least edge coloring conjecture. Okay, so these are involved applications of the LLL, where the probability space. So this has to do with least edge coloring hypergraphs. Okay, so you're trying to color hypergraphs, edge color hypergraphs. Sorry, multigraphs. I'm sorry. Okay, and the way you do it is that you sample. I mean, to give color, let's say, red to some vertices of the graph. What you do is you sample from a hardcore distribution, so from a distribution over the matchings of the graph. Because matchings do not have edges that share vertices. To get a proper coloring, one way to do it is to sample a matching for each color. Okay? And he kind of analyzes a procedure based on the local lemma that using Q samples, one for each color, for the matchings of this graph. Okay? So the idea here is that these distributions have the property that correlations decay with distance. So basically, if you look at, at the color, what is the probability that this edge is in the matching, conditional that an edge far away is in the matching? What is the probability? If those two edges are far away, then the correlations basically decay with distance, and this marginal is basically the unconditional marginal. So this is what he used in his analysis of the existential local lemma. But how this translates to when you come up with an algorithm for this application is basically because correlations decay with distance, you can kind of come up with an algorithm that locally regenerates this measure without sampling the whole thing. So I told you that a trivial way to make mu and mu equal here would be to sample from the new distribution. So when correlations decay with distance, basically you don't have to resample everything. You just need to make local moves. So this is a way where this kind of interpretation is useful. Did that make sense? Okay. I mean, I'll be more concrete next time. But yeah, that's all I had for now.